Right now, in Jinzhou Bay off the coast of northeast China, workers are building a full international airport in the middle of the sea. Not near the sea, not beside it, in it. They dredged the seabed, piled in fill material, built a 20.1 square kilometer island from scratch, and are now laying runways, pouring terminal foundations, and connecting the whole thing to the mainland by road and metro rail. The project is called Dalian Jinggawan International Airport. The official cost figure from Liaoning provincial authorities in 2026 is 50.9 billion yuan. That is roughly $7 billion. You may have seen it reported at $4.3 billion. That number is outdated. The real figure is nearly double, and the real story is even bigger than that. Before we get into it, if you enjoy videos like this, hit the like button right now. These take a serious amount of research and time to put together, and every like pushes this to more people who would love it. Subscribe if you haven't already, and turn on notifications so you don't miss what's coming next. Now let's get into it. Here's the thing. When most people hear artificial island airport, they picture a flat slab of concrete dropped into shallow water. A neat engineering trick. A curiosity. What is being built in Jinzhou Bay is something else entirely. It is a 20.1 square kilometer platform designed to handle 43 million passengers a year in its first phase alone, with long-term plans to push that number past 80 million. For context, 80 million passengers a year would put it in the same league as some of the busiest airports on the planet. And it is being built somewhere that 20 years ago was open water. To understand why China decided to build an airport in the ocean, you have to understand the problem it is trying to solve. Dalian already has an airport. It is called Zhou International Airport, and it sits inside the city. That used to be fine. Dalian was a smaller city with a smaller airport and plenty of open land around it. But cities grow. Dalian grew fast. Buildings went up around the airport. Roads were built. Neighborhoods expanded. And over time, the airport found itself completely surrounded by urban development on every side. There is no room to add a runway. There is no room to expand the terminal. Every time an aircraft takes off or lands, it flies directly over dense residential areas, which means noise complaints, height restrictions, and strict limits on how many flights can operate each day. The city needed a new airport, but there was no land left to build one on. So the engineers looked the other direction. They looked at the water. Jinzhou Bay sits just offshore from Dalian's western coast. The water is relatively shallow in certain areas. The distance from the city center is manageable, and crucially, an airport built on a man-made island in the bay would have completely open airspace above the water. Aircraft could approach from the sea and depart over the sea. No neighborhoods underneath the flight path, no height restrictions from surrounding buildings, no noise complaints from people trying to sleep. The offshore location solves almost every problem the existing airport has. It also creates a completely different set of problems. We will get to those. The decision was made, approvals were granted, and the project began. The target is a world record. When complete, Dalian Jinggawan will be the largest airport ever built on reclaimed land. That is not a marketing claim. No other airport built on an artificial island comes close to 20.1 square kilometers. Kansai International Airport in Japan, which opened in 1994 and was itself a landmark of offshore engineering, sits on a smaller island. Hong Kong International Airport, which opened in 1998 and has been one of the busiest cargo hubs in the world for decades, was built on a reclaimed platform in the Pearl River Delta. Both of those airports proved the concept works. Both of them also showed exactly how hard it is to keep a man-made island stable over decades. More on that in a moment. First, let's talk about what is actually being built here, because the scale is hard to picture. The island itself covers 20.1 square kilometers. That is roughly the size of 2,800 American football fields laid side by side. On that island, the first phase of the project includes 2 runways, a terminal building of approximately 500,000 square meters, a dedicated cargo zone, maintenance facilities, roads, drainage systems, emergency infrastructure, and all the support buildings an international airport requires. The northern runway is planned at 3,600 meters long, built to what is called 4F standard. That is the highest category in international runway classification. It means the runway can handle the largest commercial aircraft flying today, including the Airbus A380. The southern runway is planned at 3,400 meters, built to 4E standard, which handles the next tier of wide-body jets. The two runways are separated by approximately 2,500 meters, which is wide enough for them to operate completely independently of each other. Two aircraft can land or take off at the same time, without either runway affecting the other. That matters for capacity. One runway can only handle so many aircraft movements per hour. Two independent runways running at the same time roughly doubles the throughput. Phase 1 targets around 330,000 aircraft movements per year. When the airport eventually reaches its long-term build-out of 4 runways and a terminal of approximately 900,000 square meters, it is designed for 80 million passengers annually. Think about that for a second. The terminal in Phase 1 alone is 500,000 square meters. That is bigger than many cities' largest shopping malls. The full long-term terminal at 900,000 square meters would be one of the largest single airport terminal buildings on Earth. But before any of that can be built, the island itself has to be made solid enough to hold it. Here is where it gets uncomfortable. Building on reclaimed land is not like building on solid ground. When you dredge material from the seabed and pile it into open water, what you get is not a stable platform. What you get is a loose, wet, compressible mass that wants to sink. The seabed underneath is soft sediment. The fill material placed on top is not much better in its initial state. Under the weight of the fill, the sediment below compresses slowly over time. The fill itself compresses. The whole thing settles. An airport runway cannot settle unevenly. If one section sinks 2 centimeters and the section next to it sinks 5 centimeters, the runway surface develops a slope. That slope gets worse over time. Aircraft landing at high speed on an uneven surface is not an acceptable outcome. So the engineers have to deal with the settlement problem before they build anything permanent on the island. The way they do it is through a combination of techniques that have been refined over decades of offshore construction. First, they install vertical drains into the soft sediment below the island. These drains are essentially thin plastic tubes pushed deep into the ground at regular intervals. They give the water trapped inside the sediment somewhere to escape to. When you then place a heavy surcharge load on top of the fill, the weight squeezes the water out through those drains and the sediment compresses. This process is called consolidation, and the point is to force the ground to settle now, under controlled conditions, before any runways or buildings are placed on it. The surcharge load is usually extra fill material piled higher than the final planned level. You build the island up higher than you need it, let it settle, measure how much it settles, then remove the excess and build your structures on what is left. The settlement does not stop completely. It continues for years at a decreasing rate. The engineers model it, monitor it, and design the structures to tolerate the small residual movement that continues after construction. At Dalian Jingawan, as of May 2026, the main reclamation work was reported complete. That means the island shape exists, the fill is in place, but the ground treatment work underneath was only about 58% done at that point. The deep treatment of the soft seabed sediment, the installation of stone columns and piling to reinforce the ground, the surcharge loading and monitoring, all of that work takes years. It cannot be rushed. The surcharge work for both runways was reported complete, which means those areas have been preloaded and are in the consolidation and monitoring phase. The terminal pile foundations were approximately 84% finished, and the underground sections of the terminal structure were complete. That construction status tells you something important about how these projects work. The island looks finished from the air. The shape is there. But the real work, happening right now, is invisible. It is happening meters underground, in the slow compression of sediment under load, in the driving of thousands of piles through soft ground to reach solid bearing layers below, in the monitoring stations that record settlement data continuously to confirm the ground is behaving as the models predicted. 1,000 workers, more than 100 large machines, 103 active construction sections running at the same time across the terminal site alone. That is the scale of what is happening on this island right now. Let's talk about the terminal, because it is a project within the project. A 500,000 square meter terminal is not just a big building. It is a small city with a roof. It has to move tens of millions of passengers through check-in, security, passport control, departure gates, arrivals, baggage claim, and ground transportation connections, all without creating bottlenecks that back up the entire system. The design of the passenger flow matters as much as the size of the building. An airport terminal that is big but badly laid out creates chaos. Passengers miss flights. Airlines delay departures, waiting for passengers who are stuck in a queue somewhere inside a building that is too confusing to navigate. The Dalian Jingawan terminal is designed with that in mind. The building is being constructed in 103 simultaneous sections, coordinated by digital management systems and crane camera networks that track progress and flag conflicts across the entire site in real time. That level of coordination is necessary when you have that many workers and machines operating in close proximity. Without it, you get delays, collisions, material shortages in one section while another section has too much, and the kind of cascading problems that push projects years past their deadlines. The terminal also has to function as the interface between the island and the mainland. An airport on an island is useless if people cannot get there. The connectivity plan for Dalian Jingawan includes 3 separate cross-sea access routes, road links to the mainland highway network, and integration with the Dalian metro system. 3 routes matters for resilience. If one bridge or tunnel is closed for maintenance or damaged in a storm, passengers and cargo can still reach the airport by another route. A single access point is a single point of failure, and for an international airport handling tens of millions of passengers a year, a single point of failure is not acceptable. The metro connection is particularly important. Dalian is a city of several million people. Getting from the city center to an offshore airport by car means crossing water, which means bridges or tunnels, which means travel time. If the metro can carry passengers directly from the city center to the terminal in a reasonable time, it reduces road congestion, reduces parking demand on the island, and makes the airport accessible to people who do not own cars. Metro connectivity is one of the factors that separates airports that work well from airports that are always congested. Now let's talk about cargo, because that is where the strategic logic of this location becomes clear. Phase 1 of the airport is designed to handle 550,000 tons of cargo and mail per year. The dedicated cargo zone in the first phase handles approximately 275,000 tons, with room built in for expansion as demand grows. Those numbers matter because of where Dalian sits on the map. Dalian is in northeast China on the tip of the Liaodong Peninsula, pointing directly toward the Yellow Sea. Japan is roughly 900 kilometers to the east. South Korea is closer. The major manufacturing and export regions of Northeast Asia are within short flying distance of Dalian. An airport with serious cargo capacity in that location is not just an airport. It is a logistics hub connecting Chinese manufacturing to Japanese and Korean markets and to the global shipping lanes that run through that part of the Pacific. The broader plan around the airport reflects that logic. An 81.71 square kilometer economic zone is planned around the project. That is not just the airport itself. That is a planned district of logistics warehouses, cargo handling facilities, maintenance operations, hotels, and advanced manufacturing, all clustered around the airport's cargo and passenger operations. The airport is the anchor. The economic zone is the multiplier. The theory is that if you build the airport, the businesses that depend on fast air connectivity will follow. That theory has worked in other places. It has also failed in other places. We will come back to that. Here is the thing about building an airport on a man-made island in the sea. The engineering challenge does not end when the airport opens. It starts a new phase. Kansai International Airport in Japan is the cautionary example. It opened in 1994 on an artificial island in Osaka Bay, and from the moment it opened, it began to sink. The engineers knew it would settle. They planned for it. But the settlement was faster and more severe than the models predicted. In the first decade, the island sank by about 8.2 meters in some areas. The airport has spent hundreds of millions of dollars on remediation, raising the seawall, monitoring the settlement continuously, and adjusting structures to compensate for the ongoing movement. Kansai still operates. It is a functioning international airport, but it is an airport that requires constant, expensive attention to keep it that way. Hong Kong International Airport, which opened in 1998 on reclaimed land at Chek Lap Kok, has had a better experience. The ground was prepared more thoroughly before construction. The settlement has been within acceptable limits. Hong Kong's airport has become one of the world's busiest cargo hubs and a major passenger gateway. It proves that offshore airport construction can succeed at scale. The difference between Kansai and Hong Kong comes down largely to ground preparation. The more work you do before you build, the less the ground moves after. That is exactly what the Dalian construction team is doing right now, with the deep ground treatment work that was 58% complete as of May 2026. They are spending years and billions of yuan doing the invisible work underground that will determine whether this airport performs like Hong Kong or like Kansai 20 years from now. But settlement is not the only long-term risk. Dalian sits in a part of China where sea ice is a real operational concern. The Yellow Sea and the waters around the Liaodong Peninsula can freeze in winter. An airport island surrounded by sea ice faces structural loads on its seawall that a tropical offshore airport never has to deal with. The design has to account for that. The seawall has to be built to resist the pressure of ice forming against it and the impact of ice flows moving with the current or wind. Then there is saltwater corrosion. Every metal component, every concrete structure, every drainage pipe and cable conduit on that island is exposed to a saltwater environment. Salt accelerates corrosion dramatically compared to inland conditions. The maintenance program for a coastal airport is more intensive and more expensive than for an inland one. Concrete mixes have to be formulated to resist chloride penetration. Reinforcing steel has to be protected with coatings or with cathodic protection systems. Drainage has to be designed so that saltwater does not pool against structural elements. None of this is impossible. All of it adds cost and complexity to the operational budget that will run for the lifetime of the airport. Sea level rise adds another layer. The airport is designed and built to current sea level standards. The seawall height is calculated based on current storm surge data and current tidal ranges. As sea levels rise over the coming decades, the margin between the top of the seawall and the water level during a major storm gets smaller. At some point, the seawall will need to be raised. That work is expensive and disruptive to airport operations. The engineers know this. The design includes what the project describes as intelligent flood control systems and water recycling infrastructure. Whether those systems prove adequate over a 50-year operational life is something only time will answer. Fog is also a factor in Jinzhou Bay. Dense sea fog reduces visibility and forces airports to operate under instrument flight rules, which limits the rate at which aircraft can land and take off. Dalian's coastal location means fog events are more frequent than at inland airports. The airport's instrument landing systems and air traffic management infrastructure have to be designed for high-frequency, low-visibility operations. That is a solvable problem. Modern airports handle it routinely, but it adds to the operational complexity of a facility that already has more moving parts than a standard inland airport. The environmental commitments for the project are stated as near zero carbon operation, water recycling throughout the facility, and zero wastewater discharge into the bay. Those are significant claims. An airport handling 43 million passengers a year in Phase 1 produces substantial waste, uses large amounts of water, and consumes significant energy. Meeting those targets requires purpose-built infrastructure from the ground up, not retrofitted systems added after construction. The design incorporates them from the start. Whether the airport actually achieves those targets when it opens and operates at full capacity is something that will be measured and reported after the fact. The targets are real. The verification comes later. Now let's step back and look at the demand question, because a $7 billion airport is only worth building if enough people actually want to fly from it. Dalian is a major city. It is one of the most important port cities in northeast China. It has a significant industrial base, a large population, and established trade relationships with Japan and South Korea. The existing Zhuhaizi airport was handling substantial passenger numbers before its expansion limitations became a serious constraint. The demand for more capacity is real, but 80 million passengers a year is a very large number. For context, Chicago O'Hare handled about 80 million passengers in 2023. Los Angeles International handled about 88 million. Those are among the busiest airports in the United States, serving metropolitan areas with populations of many millions and functioning as major connecting hubs for transcontinental and international flights. Dalian is a large Chinese city, but reaching 80 million passengers a year requires either massive growth in Dalian's own origin and destination traffic or a strategy to capture connecting traffic from other routes, or both. The long-term capacity target is a planning horizon number. It represents what the airport is designed to be able to handle if demand grows to that level. Phase 1 at 43 million is the near-term target, and that is a more credible near-term figure given Dalian's existing traffic base and the growth trajectory of Chinese aviation overall. Chinese domestic air travel has grown steadily for 2 decades. The middle class has expanded. Business travel has increased. International routes to Japan and South Korea are natural fits for a Dalian hub. The 43 million target for Phase 1 is ambitious but not implausible. The 81.71 square kilometer economic zone around the airport is the piece that could change the math significantly. If that zone succeeds in attracting major logistics operations, cargo-dependent manufacturers, and international businesses that need fast air connections to Northeast Asia, it generates its own traffic. Companies that locate in the zone fly their goods, their executives, and their clients through the airport. The airport generates the economic activity, and the economic activity generates the airport traffic. That loop, when it works, is what turns a regional airport into a hub. It is also the loop that has failed in other places. There are airports around the world built on the premise that economic development would follow, where the development never came. The airport sits underutilized, the economic zone fills with storage facilities instead of high-value manufacturers, and the project becomes a symbol of overbuilding rather than strategic vision. China has built infrastructure that exceeded initial demand and eventually grew into it. China has also built infrastructure that never found its demand. Dalian Jinggawan is too early in its construction to know which story it is. What is not in doubt is the engineering ambition. As of May 2026, the island exists. The reclamation is complete. The piles are going into the ground at 84% completion for the terminal foundations. The runways have been preloaded and are in the settlement monitoring phase. The construction workforce of more than 1,000 people and over 100 large machines is active across 103 simultaneous construction sections. The metro and road connections are being planned and built in parallel. This is not a proposal. It is not a rendering. It is a construction site in the middle of a bay, and it is moving. The scale of the coordination required to build something like this is worth pausing on. You have reclamation engineers managing the island formation and seawall construction. You have geotechnical engineers monitoring settlement data from hundreds of sensors embedded in the ground. You have structural engineers driving piles through soft fill to reach bearing capacity deep below. You have terminal architects and construction managers running 103 simultaneous building sections. You have transport planners designing the bridges, tunnels, and metro lines that will connect the island to the mainland. You have environmental engineers designing the drainage, water recycling, and flood control systems. All of those teams, all of that work has to be coordinated so that the pile driving does not interfere with the settlement. Monitoring. The terminal construction does not block the drainage installation, and the road connections are ready when the terminal is ready. That coordination is managed through digital construction management systems that track every section, every machine, and every milestone in real time. The crane camera systems that monitor the terminal construction site give supervisors a live view of what is happening across all 103 sections simultaneously. When a section falls behind, the system flags it. When materials are needed, the logistics are coordinated to deliver them without blocking other active sections. This is not how airports were built 30 years ago. This is how you build a 500,000 square meter terminal on an artificial island in a bay without the whole project collapsing into delays. The comparison to Kansai and Hong Kong is worth returning to one more time, because those two airports define the range of possible outcomes here. Kansai cost Japan enormous sums in remediation after opening. The settlement was worse than predicted. The seawall required raising. The operational costs have been higher than planned for decades, and yet Kansai still operates. It handles millions of passengers a year. It serves Osaka and the Kansai region. The engineering problems were serious, expensive, and ongoing. They were not fatal. Hong Kong took the lessons of Kansai and applied them. More thorough ground preparation, better settlement modeling, more conservative design margins. The result was an airport that has operated reliably for more than 25 years, handled enormous cargo volumes, and become one of the defining pieces of infrastructure in the Pearl River Delta economy. Dalian Jingawan is being built with knowledge of both. The ground treatment work that was 58% complete in May 2026 represents exactly the kind of investment that separates Kansai's outcome from Hong Kong's. The engineers are not in a hurry to lay runways on ground that has not finished settling. They are doing the work that has to be done before the visible construction can proceed with confidence. The northern runway at 3,600 meters and 4F standard will handle the largest aircraft flying today. The Airbus A380, which requires a 4F runway, can carry more than 800 passengers in a high-density configuration. A single A380 flight represents more passenger revenue than 3 or 4 narrow-body flights. For an airport trying to attract long-haul international routes, the ability to accommodate that aircraft matters. The 4F designation is not just a technical specification, it is a signal to airlines that Dalian Jingawan is designed for the biggest operations in global aviation. The southern runway at 3,400 meters and 4E standard handles the Boeing 777, the Airbus A350, the Boeing 787, and the full range of wide-body jets that operate the majority of international long-haul routes today. 2 runways of that caliber, separated by 2,500 meters for independent operations, give the airport the capacity to run continuous simultaneous arrivals and departures at the rate required to serve 43 million passengers a year. The cargo operation deserves one more look. The 550,000-ton annual capacity in Phase 1, with the initial dedicated cargo zone handling approximately 275,000 tons, positions Dalian as a serious air cargo hub for the region. Air cargo is not the same business as passenger aviation. The economics are different, the customers are different, the operational requirements are different. Air cargo needs fast ground handling, large warehouse space, customs facilities, and direct connections to ground transport for onward delivery. The design of the cargo zone at Dalian Jingawan incorporates all of those elements. The proximity to Japan and South Korea, 2 of the world's largest export economies, gives the cargo operation a natural customer base that does not depend entirely on Dalian's own import and export volumes. When you add the 81.71 square kilometer economic zone to the cargo operation, you start to see the full strategic picture. The airport is the center of a planned logistics and industrial district that is designed to capture a share of the trade flows between Northeast China, Japan, and South Korea. The reclaimed island is not just an airport, it is the anchor of a new economic geography for that part of the Yellow Sea coast. Whether that geography materializes as planned is the open question. The engineering is proceeding. The construction is on track by the metrics available as of mid-2026. The island exists, the piles are going in, the terminal is taking shape, and the runways have been preloaded and are being monitored for settlement. The hard and visible work underground is more than halfway done. But the final judgment on Dalian Jingawan will not come from a construction progress report. It will not come from a ribbon-cutting ceremony or a record certification for the world's largest artificial island airport. It will come from what happens in the years after the first flight lands. Whether the ground holds steady under the weight of fully loaded aircraft operating day after day. Whether the seawall stands through the sea ice and the storm surges. Whether the cargo zone fills with real logistics operations or sits half-empty waiting for tenants. Whether the metro line actually gets passengers to the terminal in time for their flights. Whether 43 million passengers a year actually want to fly through Dalian. The engineers have done the math. The construction crews are doing the work. The island is there. Now the question is whether everything built on top of it will prove them right.